Okay, ELE 111, Chapter 7, Part 1, actually 7-1, Part 2 in this video, where we're still looking at series parallel relationships. And I want you to start looking at the drawing on the left, and you'll see that this resistor is completely in series with the rest of the circuit. Usually, when we calculate total resistance, we cut the power supply out and we look into where the power supply is, and that's how we see that this particular resistor is in series with the supply. Now, usually we start at the opposite end, which is over here, and we start compressing. Now, this is a tricky problem to see in some cases because that's the same drawing right there to the right. They've taken R5 and they've shifted it up to produce this relationship. Can you see what that is? That's R4 in parallel with R5. So that makes it very, very reducible. The top portion up here is R2 and R3 in parallel, and to reduce them, you would simply use the R total formula, R4, R5, multiplied, divided by the total of R4 and R5, product over sum. You've been through this before. We've looked at it. So if I was solving this circuit, I would create multiple drawings of this circuit right here, located to the right. I would make multiple drawings of it. My first drawing would look like this. It would combine R2 and R3 together to form R23. And then I would make a second drawing, and this is R1 right here, and this is R5 and R4. Then I would make a second drawing which would combine R4 and 5 and R2 and 3. You see what we've done? We've boiled the circuit down into a series circuit. And our eyeball is sitting here looking in, and we've gone to the outside. I can't overstress how we move to the outside to get anything done. Okay? Keep that in mind as we move forward. Here's what I say is it's a pretty big circuit. It's a pretty big circuit, and it's kind of messy. I can see that these two resistors are in series, like a snake. We've said that before, like a snake. That particular snippet from that X to that X, or from B to C, are in series. Okay? Now, what else is going on here? This resistor here, you see, I'm out here reducing back because my ohm meter is sitting between these two terminals, and I have to get out here to the outside to look at this. And I see the R2 and 3 are in series, and what I'm going to do is methodically break down this circuit. There's 2, 3, and it leaves R4 there. Sorry, the drawing tools are not that fantastic. And we've got R6 and R5. And they're all sitting out here connected together, and we've got R1 out here. Now, this is definitely, this part is definitely in parallel. And if I reduce it, we call this R6 and R1. Then this is R2, 3, and this is 2, 3, 4, and this is R5. Now, you might think that these two resistors are in parallel, but they're not in parallel. You see, this component is in the way. So R2, 3, 4, and R5 are actually in series. You can slide R5 up, or you can slide 2, 3, 4 down and add them. And what does that do for us? What does that do for us? That takes what we had here a minute ago, I can't rub that out for some reason. Must be under the umbrella of the other drawing. Very interesting. Okay, so we've got R6, R2, 3, 4, and R5 sitting like this. And once we add these, we end up with a parallel circuit. R2, 3, 4, and 5 compress to be in parallel. So what you're starting to see is things go from series to parallel, or from parallel to series, but they flip back and forth. It's here's a parallel, reduce it, pick up a series. Or here's a parallel that reduces to another parallel. But there are only two choices. The only two choices you have are series or parallel. There is a series parallel circuit, but you have to continue to break down series and parallel relationships. Okay, here's an interesting problem. 3 points, A, B, and C. C is located out here on the end, so we'll leave it right there. And what you've, let me erase a little bit here. Okay, what you've got is a triangle. Now I'm going to give each of these things a value. 1K, 2K, and 3K. And this is just 3 resistors all hooked together. They're not in series. They look like they are. They're not in series. What depends on what's in series is where is my meter. So if I hook my meter between B and A, if I hook my ohm meter up between B and A, then I have established a relationship of where the meter is going to stick. And because of that, this resistor here that's in front of the meter leads directly in line with A and B cannot move. So we have to go out here further away from the circuit to be able to compress resistance. So remember, this relationship that we're looking at right here is going to remain in the green. It's going to remain, and we're going to look at the relationship of these two resistors. Forget about the fact that that's called point C. These two resistors in blue are in series with each other, located away from the ohm meter, located away from R1. So what you end up with is R1, and you've got R2 and R3 that are in series. That's 5K. That means that you have 1K and you have 5K in parallel. So to resolve that, you have R1 times R23 divided by R1 plus R23. You see, that's how that game works. And if you compute this, 1K times 5K divided by 1K plus 6K, you get 5/6. That's 5 over, oh, sorry. Let's see, what do we got there? 5 plus 1, 5. 5 plus 1 is 6. So we've got to delete and put back the 5, and we get 5/6, okay? K ohms. So we've got 5/6 of whatever we calculate. Let me grab my calculator here. 5 divided by 6. We've got 833.33 ohms, which is less than 1,000, which is the smallest of the two resistors. So, what am I trying to say? I'm trying to say that the resistance between RAB is 833.33 ohms. Okay? That's what I'm trying to say. Now, if I move my meter around, the resistance will change for any given object. All right? And I'll draw you a little example, or at least I'll tell you a little example. If I had 5 resistors sitting on the table and I went and measured each of them, they would all give me different values. You know why? Because they're all independent and different valued components, okay? What we're trying to do here is move the ohm meter around. I'm going to take the ohm meter away from this area, and I'm going to move it to a different spot. I'm going to move the meter over here. We'll do it in green. We'll do it in green. We'll do it in green. In a moment, we'll do it in green. There's the ohm meter. It sits across RBC. Will RBC be anywhere near RAB? It will definitely be different because now the meter is frozen in place, which locks these two components that you see in red circled. The meter and the 3K resistor cannot be moved until everything to the outside, which is here, has been compressed. Well, if we learned anything about our first example, we learned that the resistance of these two components, which are 2K and 1K, become 3K. They are in series. So we've got a 3K in parallel with an ohm meter that sits near R2, which is 3K. And we don't really need to do the math here. We've got two resistors, equal value. They reduce to 1.5 K ohms, 1.5 K ohms. That's product over sum, okay? This is R13. And we get RT is 3K times 3K over 3K plus 6K. And you get 9 on the bottom. And let's see, 6, 7, 8, 9. 3 times 3 is 9. 3K and 3K. We got 3K and fix it. 3K. That puts 6 on the bottom. That puts 6 on the bottom. That puts 9 on the top. That produces 1.5 K ohms. Okay? Which is not the same as RAB. This is RBC. So location, location, location. Location is everything for an ohm meter. Depending on where you put it in the circuit, the resistance changes. Okay? Now, in a unique situation where parts and the world aligns just perfectly, it's possible to have more than one value be identical, but that doesn't mean that they are the same. Okay? So the next thing we're going to do is we're going to clean this drawing up a little bit, take away the blue, and 1K and 2K and 3K. This time, with the given values that are shown, we're going to put the meter here. Again, where you put the meter, if there's a resistor directly in parallel with the meter, which there is right here, R3 cannot move, okay? So we go to the outside here in the black circle, and we've learned that 1K plus 2K out there produces 3K, and it's connected to another 3K. Yeah. Another 3K out here, and the meter is stuck out here. So what we have is 3K in parallel with 3K, which produces 1.5 K ohms. Our total is 1.5 K ohms. So although this doesn't appear to be a circuit of incredible symmetry, it still can be contained with the ohm meter, and where you move the ohm meter determines what the resistance of the circuit and what the relationship between the parts are.